Hey guys, and welcome back to another video on the channel. In today's video, we're going to be going over the introduction to the Schwarz radius of pretty much a black hole. So, what the Schwarz radius of a black hole is pretty much the distance from the center of the singularity to the event horizon. So, pretty much, the event horizon is pretty much the point at which you pass. Once you pass that, you pretty much get sucked into the black hole. So, it's pretty much the point of no return. And yet, the Schwarz radius is the distance from the singularity to the event horizon. So, what we're going to be doing is pretty much showing you how to calculate it and pretty much where the formula comes from for it. So let's just get straight into it. So what we need to know before we even start thinking about calculating this is understanding time dilation. So I've covered this in the past that pretty much all time is relative to how fast you're traveling through space. So for example, what someone sees compared to someone else might be completely different depending on how fast they're going. And you can calculate most of this with this formula here. T equals TO over the square root of 1 minus V squared over C squared. So T would be your dilated time and TO would be your proper time, depending on who's observing what, pretty much, okay? We also know that from the theory of general relativity that time difference depends on your location in space too. So pretty much how gravity affects you. Because gravity is pretty much proportional, or it depends on pretty much mass in space. So mass curves space-time, which is pretty much the effect of gravity. So how strong gravity is around you relative to your position in space, that can be a factor as well. If you live in a strong gravitational field, time runs slower for you. So what we're going to be doing is using this formula here and this fact from general relativity to try and get pretty much a picture of where we need to go to pretty much look for this formula for the Schwarz radius of a black hole. Okay, so mass curves space-time, which creates gravity. More mass, more gravity. The formula for the escape velocity can be seen below. Now, we need this to pretty much account for the mass in time dilation. So, if you want to escape Earth, all you got to do is plug in the mass of the Earth in here, Newton's gravitational constant, and pretty much the radius or distance from the center of the Earth, okay? And that will give you the velocity you need to escape, pretty much. So we've got to account for this into our time dilation formula. So, using this and the formula for time dilation, the formula for time dilation accounting for the mass of an object can be found. So pretty much I'm going to rearrange my formula up here. So what I'm going to do is square both sides. So that'll give me V squared equals 2 times the Newton's gravity constant times the mass all over the radius. And then I've got this formula here. Now all I've done is rearrange it. So I've divided both sides by, I've timed both sides by the square root of 1 minus V squared over C squared to get this expression here. And all I'm going to do is replace pretty much, let me get the pen out, make sure it's the right color. So all I'm going to do is substitute this guy into here pretty much, and it gives me this following formula. So now I've got time dilation accounting for the mass of your object you're escaping from pretty much and its distance, okay? Now, condition for a black hole. For a black hole, the Schwarz radius is at the edge at which time comes to a stop. So pretty much you've got your singularity here and you have your event horizon, okay? Now imagine this in 3D. When you get here, time needs to stop pretty much. So what we've got to do is know when TO equals 0. So in other words, we have this formula here, and I'm just going to rub out this really quickly because it's going to get in the way. Rub that out. We need to know when this is equal to 0. Now, t can't be 0, so we need to know when this term needs to be 0. So in other words, if t needs to be 0, we need to know when this is 0. And the only way this can be 0 is when this term here is equal to 1 pretty much. So all you do is times both sides by r, and that is the formula for the Schwarz radius of a black hole. Okay, because it's accounted for the condition for a black hole. And that's pretty much where the formula comes from. So the Schwarz radius is equal to twice Newton's gravitational constant times the mass divided by the speed of light squared. So, introduction to the Schwarz radius. The Schwarz radius is the distance from the center of a black hole below which nothing can escape, pretty much the event horizon. So, if we imagine this is pretty much the event horizon around a singularity here, and this is its distance here. So, this is the singularity, and that's the Schwarz radius pretty much. So, once you go past this curve here, once you're less than the Schwarz radius, you get sucked into the singularity pretty much, okay? And that's the event horizon there. So the Schwarz radius can be calculated via this equation we've just derivated. So the Schwarz radius is twice gravitational constant times mass all over the speed of light squared. Okay. Yeah. Newton's gravitational constant is 6.67 times 10 to the negative 11 newtons times meter squared inverse kilograms squared. M is mass, given in kilos. C is the speed of light, which is 3.0 times 10 to the 8 meters per second, and R is the Schwarz radius. Now, I put a little S there for subscript to indicate Schwarz radius rather than just radius, and it's given in meters. Okay, so calculating the Schwarz radius for objects. So it doesn't just work for black holes. What we can do is calculate the Schwarz radius for anything, pretty much. So, for example, if we calculate the Schwarz radius for, let's say, the sun, we've got the mass of the sun here. So it's 2 times 10 to the 30 kilograms. We have our formula here. Plugging in our numbers. So we plug in our gravitational constant, the mass of the sun, and the speed of light. And we get a Schwarz radius of this. So what does this number actually mean? So if the sun was compressed to have this radius around it, it can be considered a black hole pretty much. Okay? So how to make a black hole. Any object that can be compressed down to the size of its Schwarz radius can become a black hole. So with a black hole, most of the time, if I just get my pen out again. So most of the time with a black hole, the singularity is here and the event horizon here. And that is your Schwarz radius. So the Schwarz radius is the minimum distance it needs to be. So in that previous example, if we had the sun and its Schwarz radius was, I think it was like 3 kilometers, so 3,000 meters roughly. That is the minimum distance it needs to be a black hole. Now, most black holes, the singularity is smaller than the Schwarz radius. So that's just the minimum distance it needs to become a black hole. Okay? So I'm going to rub that out because it's going to get in the way of my other stuff. Oh, I messed there. Okay, so from the previous calculation, if the sun maintained its mass and was compressed down to its Schwarz radius or smaller, it would become a black hole in theory. But this isn't the only way to create a black hole pretty much. So black hole depends a lot on mass. So if you keep adding mass to an object, it will become a black hole. And this can be calculated with this formula. Assuming now this formula, we're assuming it's a sphere, because most of the time we'll be dealing with planets or stars and stuff like that. So mass is equal to volume times density. So in other words, the mass of a sphere is 4/3 times the density pi r cubed. Okay? If we rearrange this, we can see the radius is the cube root of some constant times mass. Okay? So in other words, the radius is proportional to the cube of the mass. Okay? Now, the Schwarz radius is a constant here, and mass depends on the object. So the Schwarz radius is proportional to the mass. So the Schwarz radius of an object is linear, while the radius of a normal object is the cube root. This means over time, the Schwarz radius will overtake the radius of an object as the mass increases. So what I'm meaning is, if I double the mass, the Schwarz radius doubles, but the radius itself only increases to like 1.6 if it was like doubled. So what I'm pretty much saying is, if I get my pen out again, where is the pen? I lost the pen. So the Schwarz radius would start down here. So Schwarz radius, and your normal radius would be up here. So just R, but it's a cube root, so it would start to look like this. But the Schwarz radius is a linear line. So eventually, over time, it will begin to overtake it. So as your mass increases, so let's say this is just as mass increases, the linear trend will increase and the radius will slowly increase, but not as much as the Schwarz radius. So if you just kept adding mass and mass to an object, eventually it would turn into a black hole. Okay? Yeah. And that's about it on this video. So that was an introduction to the Schwarz radius of a black hole. I hope you enjoyed it. If you did, like and subscribe, and there'll be more videos on black holes coming soon.